Hello. Hello, Preeti. Am I audible?
Yes, sir.
Okay. So, do you know the exam schedule, university exam schedule for your winter examination?
Yes, sir.
Because the tentative dates are from 28th December to 26th January. Your winter 2020 examination duration that is declared by the university. Okay. Then your PLM starts from 28th December to 28th December tentative. Then most important thing is that our class test 2 will be scheduled from 10th, 11th and 12th December. So up to 10th December, we are setting the target such that anyhow we have to complete our all the 6 units. Okay. So please note down this. Your class test 2 schedule is from 10, 11 and 12 December, and after 12 and from 15 to 20 December your practical submission will be there. Okay, as well as your TEC submission will be in between 15 to 28 December. Okay, again, your class test 2. So your class test 2 is also MCQ type, and we have to conduct a TEC that could be a assignment type. Okay, so these are the guidelines we have received from the respected HOD sir in the last meeting. So everyone must be aware about this. Okay. Then so in this week, I am going to upload uh, all the practical list as well as the practical manual. Okay, on the Teams. So I request everybody please download it. Okay, and we just have few the discussion about the right practical. Okay, and the conduction of the practical. Okay, so you just do one thing. Just take one notebook, and in that notebook you just write down all the practicals. Okay, then through video demonstration I will give you the theory part of that practical and the how we are going to conduct in the laboratory and its readings. Okay, so I just upload the short videos of the each and every practical so that each and everything will be clear to you. So, and if you have any doubt after uploading or after viewing the video, short video, just 10-15 minutes for each practical, so you can see it at your end with respect to your convenient time. And if you have any difficulty, you can convey to me. So in this way, we are going to complete our practicals in this session. Okay. So if you have any query, suggestion, always welcome. Okay, so these are the guidelines that we have received from the last meeting. Okay, which is held at 2nd November 2020 in our department. Also, we have scheduled one meeting on Saturday, that is 3 years meeting at 9 a.m. Okay, I have already created a meeting on the Teams. Okay, so it is compulsory to all the students to attend this meeting because in this meeting the main agenda is that regarding the academic review. That will be the first agenda. Second one is the regarding project group formation, and third one is regarding the general discussion. Okay. So in this meeting, we are having with our respected HOD sir and the project coordinator. Okay, so if you have any queries, difficulties, so for that purpose, this meeting is scheduled on Saturday. Okay, so everybody must attend this meeting. Okay, so that was the agenda of that meeting. So again, okay, so these are the things that we have discussed in the last meeting. So if you have any query, you can ask to me or you can WhatsApp me. Okay. So now let's begin with the unit that is unit 4, stability of a system. Okay. So this unit is very important as far as your university examination is concerned, or which is very simple one as compared with the previous unit. Okay. So I just tell you the important of this unit. So in this unit, you have to prepare only two methods. Okay, so in this unit, only two methods are there, and on both the methods, 30 marks questions are always asked in the university examination. Okay, so therefore, in this unit, you have to prepare only two methods, and always 13 marks questions are asked based on each and every method. Okay, so henceforward, unit 4, 5, 6, you will find a directly 13 marks question or 7 or 8 marks, but probably one question is of 13 marks is always asked in the examination based on unit 4, 5, and 6. Okay, and these units are very scoring one. Okay, so I request everybody, please give your attention on this unit. And also my request is that you just bring the graph paper. Okay, that is our normal graph paper and the semi-log graph paper. Okay, from your nearby stores if available. Okay, because in the unit 4th we require a normal graph paper, and unit 5th and 6th we require semi-log graph paper, and without that graph we cannot solve any problem. Okay, so my humble request is that please bring the graph paper along with you. Okay. Okay. So our unit number 4th is the stability. Okay. So this unit number 1 is again divided into two parts. The first part is the stability of the control system, and in the first part we are basically dealing with the first method, that is root Hurwitz criteria, and second part is related with the root locus. Okay, so these are the two parts in the unit number 4. Okay, so we start with the stability. Okay, so everybody is aware about the stability. We always, in our day-to-day life, we always talk about the stability or the, okay, stability. Okay, so in general, what is the basic concepts of stability in our general day-to-day life? Can you anybody explain this? What do you mean by stable system or unstable system? Stability means what? Yes, anybody guess? So until now we have seen the types of the system and their time domain analysis, but we are not directly comment on whether this system is stable or unstable. Response, we have seen that if there is oscillations in the system and if they are continuous, then and if you are there, the response of the system is approaching towards infinity, then we say that our system become unstable one. Okay, but we are not directly commented on this stability part. Okay, so stability is concept of stability is defined with respect to the input and the output of the system. Okay, so I just give you the day-to-day life example. Suppose now you are, if you are after the final year when you pass out, okay, so in your class it may consist of 60 or 70 students. Okay, so all the students may not get a job at the same time. Okay, so some people may get a job uh, before their completion of graduation. Some may get a job after their completion of graduation after few years or after few months or within a few days like that. Okay, so what will happen once you get a job? Then you have your own dreams. Okay, then we say that अरे यार उसका वो उसको अच्छी जॉब लग गई, अच्छी सैलरी लग गई, तो हम लोग बोलते हैं डे टू डे लाइफ की वो स्टेबल हो गया, अभी सेटल हो गया. ओके, so therefore this stability is a term which is related with somewhat settling time, and settling time is depends on the system to system, that means person to person it may get vary. किसी को अर्ली स्टेज में मिल जाएगा, किसी को बहुत दिनों के बाद में मिलता है. Okay, so based on that we can also determine the stability. Okay, so you just understood the stability in the terms of control system. Okay, so in control system, what we have seen, we have a system and we have to determine whether this is stable. So how we are directly comment on the system stability, or what will be the concept of stability. So let's say first we discuss about the concept of stability. Okay, so let's say we have this system and this system has the transfer function g upon 1 plus minus e by h. So this will be the respective transfer function of this given system, and we know very well how to determine transfer function of each and every system. We have seen the different methods of it. Okay, so let's say again we have tested our system with the different types of input. We have applied unit step, unit ramp, parabolic input, and we have determined its time response. So let's say when input is applied to this system, let's say it is R of S. So at that time, when you apply input, you will get the output C of S. Okay, so if you see the time response of this C of T, so time response is nothing but it is the graph of C of T versus time T. Okay, so let's say if you have applied, the inputs are again classified into two types, that is bounded input and the unbounded input. You might be heard about this word in the signal science system. Okay, you have tested various types of signal with the help of this test of stability, bounded input and bounded output. So that is called as PIBO system. Okay, so let's say this is any bounded input we have applied to this given system. When you are, we say that when our input is bounded. Okay, so when bounded type of input, bounded means it is a limited one. Okay, so when such type of input is applied to given, it gets your time response could be like this. Okay, so input, what about this output? T of T versus T. What is your observations from this? again, here we say that our output is bounded output. So why we are saying that our output is bounded? Because our output is lie within certain limit. Okay, so that means we say that our system output of the system is also bounded one. So you see this in this time response, as the time increases, the oscillations in the time response may get vanish out after certain time, and after that we will get the output of the system to be remain constant with respect to time t. So that means we are getting a bounded type of output. That means within a limit we will get certain output. Okay, so therefore this type of system is known as a stable system. So in this way we can define a concept of stability. So when we say that our system to be stable, okay, so the systems are always stable when we apply a bounded input to the system and we are getting a bounded output of the system. Then the first type of systems are always said to be a stable system. And from this, we have determined the concept of stability. So stability is nothing but what? When we apply bounded input to any system, and also from that system we are getting a bounded output. Then the system is said that it is a stable system. Okay. Then second example we are getting. Okay. So let's say again, this is G upon 1 plus GH plus minus GH. So input applied to this system is again R of S. This is P of S. So let's say again, bounded input is applied. Bounded input is applied to this system. But for a given system, if you see the time response for this bounded input, this is the graph of C of S versus time t. And for this case, okay, if you are getting a output response like this way. Okay, so what are your observation in the second case? So as the time increases, okay, the oscillations in the output response are increasing, and at t tends to infinity, oscillations may reach to infinity. Okay, so that means here in the second case, as bounded input is applied, but how is the nature of your output response? It is not a bounded output, it is unbounded output. So, okay, so therefore this second system may not follow the BIBO principle. So therefore the second system is called as a unstable system. So here we are just checking the stability of the system simply by application of the input and by viewing its time response. Okay, so if a system is applied with bounded input and it gives us the bounded output, then system is said to be stable system. And if a system is applied with bounded input and it gives us a unbounded output, then the system is said that it is a unstable system. So this is a simple concept of stability. So in this way we have derived a concept of stability. Okay. So this will be our first part, the concept of stability. So you always remember BIBO type system. When bounded input is applied, we will get bounded output. Then such systems are always stable. Okay. Then next one is the second point, that is the stability in terms of its characteristic equation. Second point is the stability in terms of characteristics equation. So we will see different types of stabilities are there. So we will see one by one. But before that, we just understood this concept. Stability in terms of characteristic equation. We have seen the transfer function, and transfer function can be denoted by, it is the ratio of numerator n of s upon denominator that is d of s, or sometimes it may denoted by n of s upon q of s.
Sir.
Characteristic equation is generally denoted by d of s or q of s. Okay, and you have seen the order of the system. Okay, how to decide the order of the system? So the
Sir, screen is
highest
not
power of
visible.
Sir,
is not visible. Okay, okay. Now is it visible?
Yes, sir. Yes, sir.
Yes,
Yes,
sir.
sir.
So, so the stability in terms of characteristic equation. Okay. So transfer function is nothing but it is the ratio of numerator upon denominator. Okay. So sometimes the characteristic equation is denoted by Q of S or E of S. So any notation you can use. Okay. So up till now, from the characteristic equation, we have determined the stability. We can also determine the stability. In the previous unit, we have seen type 0, type 1 system or order of the system. So how we have determined order of the system? The order of the system is denoted by the highest power of s in the denominator. Okay, so s raised to power n, that indicates the order of the system. Okay, so s raised to power n, that indicates that is the highest power of s, that is the order of your characteristic equation. Always the denominator equation of transfer function indicates the characteristic equation. Okay, so in the previous unit, for the determining the time response is concerned, we have considered only highest power of s to be 2. We have determined time or time response of only first order and second order system. Okay, so that means when the order of the system is second order, okay, so up to second order, it is very easy to determine its time solution or time response. Okay, so as the mathematical computations are lesser for first order or second order control system, it is very easy to determine its time response or its time solution. Okay, so that means we can easily determine stability of first order or second order control system from the characteristic equation in case of first order or second order control system, because we can easily determine C of t versus time t, and from the observation of C of t versus time t, we can easily determine the whether your system is stable or unstable. Okay, but when the order of the system increases, when the order of the system increases, that means for third order, fourth order, fifth order, and sixth order. Okay, so so what about the determination of time solution of higher order system? It is a time consuming and complex process. Okay, so therefore, as it is the time consuming and the complex process, that means we cannot easily determine the time solution of higher order control system. Okay, so therefore, how we are going to comment on whether your system is stable or unstable in case of higher order control system? For that purpose, we have to go for another methods of stability. In that case, this time solution method is not feasible to determine the stability within a less amount of time. Okay, so that is why we go for another method. And this with the help of time solution analysis. Okay, so again, this stability concept of stability is divided into two parts. One is the qualitative and quantitative. Okay, so this stability analysis is divided into two parts again, qualitative and quantitative analysis. So qualitative means we can directly determine the stability from the characteristic equation. Okay, and quantitative means we are using certain different measures. Okay, so basically quantitative analysis is determined with respect to simple settling time, and here qualitative analysis is determined with respect to simple characteristics equation. Okay, so here again this qualitative analysis is denoted by the absolute stability, and quantitative analysis is dealing with the relative stability. So we are going to see the details of this absolute stability and relative stability. Okay, so always remember this absolute stability is the qualitative analysis of the system, and relative stability determination means it is the quantitative analysis of the system. So relative stability is related with the settling time of the system. Based on the settling time, we can determine whether our system is stable or unstable, and how much time it will take to settle down. Okay, and absolute stability, this can be determined from the simple characteristic equation. So without determining its solution, in case of absolute stability, it is not necessary to determine its time solution. Okay, so without determining the time solution, simply by using a characteristic equation, we can directly comment on the stability. This first type of stability is called as the absolute stability. Okay, and this relative stability is related with the settling time. Okay, then this relate, which are the measures to determine relative stability? So generally, relative stability is determined with two terms, gain margin and phase margin. While discussing about the types of controller in the very first slide, I have shown you the time response specifications and the frequency response specification. So generally, the frequency response specifications are gain margin and phase margin. So this relative stability is determined with respect to gain margin and phase margin. So these are the measures of relative stability. Okay. So this is all about the absolute stability and the relative stability. Then next, so by using this discussion, what is the basic definition of stability? How will we define as a system to be stable from this concept of stability? What do you mean by stability of a system? So basic definition of stability. When you say that your system to be stable, from this example, here we have considered two cases. The first case, here oscillations are damp out. Here in the second case, the oscillations are increasing with respect to time. Okay, so when we say that system to be stable, when the oscillations when you apply input to the given system, the oscillations in the systems are damp out with respect to time, then system is said to be a stable system. Conversely, in the second system, as the time increases, the oscillations in the systems are goes on increasing in the magnitude. Okay, and if the magnitude, okay, so therefore we say that a system to be unstable one. Then the third case possibly is that if the oscillations in the systems are constant one. Okay, so such type of oscillations are called as sustained oscillations are present. So according to that, we can define a system. So then such type of systems are called as marginally stable system. Okay, so we are going to see its step response and impulse response. So the nature of step response or impulse response is depends on the nature of the location of the poles in the S plane. Next part. Okay, basically here we can define the stability such that any linear control system that can be defined with the help of these two three example. Okay, so definition is that if the oscillations are set up in the system for a given applied input, the oscillations are damped out with respect to time. The system is said to be a stable system. Okay, and conversely, if the oscillations are increasing with respect to time, okay, in magnitude, then the system is said to be a unstable system. So this is a simple definition of stability. So it's simple how to remember it. When you apply input to the system, given system, then if the oscillations in the systems are damping out with respect to time, then the system is called as the stable system. And when you apply input to the system and the oscillations in the systems are increasing in magnitude with respect to time, then the system is called as the unstable system. So this is a simple definition of stability. Then this stability is divided into two parts: absolute stability and relative stability. Okay, stability are divided into two parts: absolute and relative. Let's try to understand the difference between absolute and relative stability. Absolute stability is a measure of qualitative analysis of the system, and relative stability is the measure of quantitative analysis of the system. Okay, so qualitative means what? Without getting a time solution, without getting a time solution of the system, how we are comment on the stability, whether system is stable or unstable. So we just determine the absolute stability simply by using the characteristic equation of the transfer function. Okay, so from the characteristic equation, we can directly comment on the stability, whether your system is stable or unstable. Okay, then in case of relative stability, we are going to determine the two measures, that is gain margin and phase margin. These are the frequency response specification, frequency response specification, frequency response specification, and with the help of this gain margin and phase margin, we can directly comment on the stability. Okay, so these are the difference between absolute stability and relative stability, and this relative stability is again related with the settling time, that is TS of the system. Okay, so if you talk about in terms of S plane, okay, so this is your S plus, and this will be J, sorry, this, okay, this is S and this will be J omega term, that is sigma plus J omega, because S is the complex quantity and it will be given by sigma plus J omega, where sigma is the real part and J omega is the imaginary part. This is the S plane. Okay, so in the S plane, okay, so how relative stability is determined? Okay, so it depends on the exactly the location of the poles in your S plane. Okay, so let's say this is first location, then second location is here a pair of complex pole. Again, next one is another pair of complex pole. So how is its time response? So if the poles are located near to the origin point O or near to the imaginary axis, so this is your imaginary axis. Okay, so how relative stability determined with respect to settling time, and on which factor this settling time is depend. Okay, so if you see the time response for such type of pole which is close to imaginary axis, so you will get the time solution like this. So this is the graph of C of t versus t. Then when you move away from this, you will get the time response could be like this. A certain amount of oscillations, okay, and for third pair of for this pole, okay, the oscillations in the system may get damp out like this, okay, and also the settling time for this ts is lesser than the settling time for this pair of pole and for this pair of pole. That means we say that in case of relative stability, this settling time is inversely proportional to 1 upon the negative real part, 1 upon the negative real part of your pole. So settling time Ts is inversely proportional to 1 upon negative real part of your pole. So that means we see that in the complex plane, okay, so in the complex S plane, how relative stability is determined. So let's say this is your complex S plane, this is sigma plus j omega. So as the location of the pole is move away from the imaginary axis, so the relative stability may get increased. So how relative stability is increased? So as the location of the poles are move away from your imaginary axis, the relative stability may get increased. So that means in order to improve the relative stability, we have to locate or the location of the real part of the pole must be moved away from the imaginary axis. Okay, so in this way your relative stability may get increased. So you just remember here, relative stability is uh, depends on the settling time. Relative stability depends on the settling time, and settling time is inversely proportional to 1 upon the negative real part of your poles. Okay, so this is all about relative stability. Okay, then now in the unit 4 we are dealing with the absolute stability determination, and in unit 5 and 6 we are dealing with the relative stability determination method. Okay, so first we see how to determine absolute stability. Okay, so absolute stability determination methods are is the Routh-Hurwitz criteria. Okay, so that is the first method we are going to see. Okay, so give the heading. Next one is the Hurwitz determinants of polynomial. Hurwitz determinant of polynomial. So here we are not dealing directly with the Routh-Hurwitz criteria, Routh array method. Okay, so before that we are going to determine first what do you mean by Hurwitz determinant. Then we see the difficulties associated with this Hurwitz determinant, and then we go for the next method, Routh-Hurwitz criteria. The difficulties of Hurwitz determinants are minimized by the Routh criteria. Okay, so that we will see first. Okay, so please note down this. So in general, the transfer function of any system is denoted by n of s upon q of s. Okay, numerator upon denominator, where q of s is the characteristic equation, and in general any transfer function can be represented by, it is b0 into s raised to power n, or here in case of numerator we may use m plus b1 into s raised to power b1 into s raised to power m minus 1 plus dash 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 up to bn. B here is m, okay, upon same way characteristic
Sir.
equation q of s here
Sir,
a0
finish
into s raised to power. Now is it visible? Yes.
Yes, sir.
Okay, so please note down this. Next point is the Harvey's determinant. Okay, so how to determine stability with the help of Harvey's determinant. Okay, so Harvey's is the name of the scientist who have developed this method. So how this with the help of this method we can determine the absolute stability of a system. So let's say transfer function of any system ratio of n of s upon q of s, and it will be represented by b0 s raised to power m plus b1 s raised to power m minus 1 plus dash 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 up to bm. Similarly, the characteristic equation q of s a0 s raised to power n, a1 s raised to power n minus 1, okay, plus dash 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 up to an. So this is the general form of transfer function. Here we have represented. So upper term is denoted by n of s and denominator term is denoted by q of s. So here this q of s is called as the characteristics equation, and the stability of the system is determined with respect to this characteristic equation of your transfer function of given system. Okay, so your characteristic equation, so this is the general form of your characteristic equation, and its order is, it is the nth order characteristic equation, because the highest power of s in the denominator is n, so therefore it is nth order characteristic equation. Okay, then what is Harvey's criteria? Okay, so for this Harvey's determinant or Harvey's criteria, it consisting of two conditions. So what do you mean by Harvey's criteria? The condition, just note down this, the sufficient condition for the Harvey's determinant is that the sufficient condition for Harvey's determinant is that the sufficient condition for having all the roots of characteristic equation, in the left half of S plane, in the left half of S plane is given by Harvey's, and this is the sufficient condition for Harvey's determinant. The sufficient condition is that the location of the roots of your characteristic equation must be in the left half of S plane. So if this condition is satisfied, your system becomes stable one. So what is the sufficient condition for Harvey's determinant? The roots of your characteristic equation must lie in the left half of your S plane. So S plane can be divided into two parts, left half of S plane and the right half of S plane. So please remember this term with respect to S plane, because all the analysis we are doing in the S domain, in the control system. Okay. So, and the stability can be determined with respect to it. Okay, so this will be your S plane. This is sigma plus j omega axis. This is your origin point O. Okay, so this could be your left half of S plane. So this is called as left half of S plane, and this will be your right half of S plane. So this is RHS and this is LHS. So when your location of the roots of your characteristic equation lie in the left half of S plane, your system is always stable. And if any one of the pole are lie in the right hand side of a S plane of your characteristic equation, so your system become unstable. So in this way, we can determine absolute stability by using a characteristic equations directly. So here in this method, we don't need to determine a time solution of your system. Okay, so simply by observing whether where is the location of the poles in the S plane. If all the poles are located in the left hand side of your S plane, your system becomes stable one. And if any one pole are lie in the right hand side of your S plane, your system become unstable. Okay, so that we will see the with the help of step response and impulse response for different location of the roots in the S plane. Okay, so we can see the types of the system, whether it is marginally stable or critically stable or absolutely stable, like that. Okay, so before that we are dealing with Harvey's determinant. So the for Harvey's determinant, the sufficient condition is that the roots of the characteristic equation, roots of characteristic equation must lie in left hand side of S plane. So this is the sufficient condition, and the necessity condition for Harvey's determinant is that आपको जो भी determinant मिलेंगे, okay, so that is called as Harvey's determinant. Okay, so Harvey's determinant अभी सब रूट्स यस लेफ्ट हैंड साइड ऑफ यस प्लेन में है, ये कैसे डिटरमाइन करोगे? फॉर दैट पर्पस दिस नेसेसिटी कंडीशन विल बी देयर and it is denoted by Harvey's determinant, and Harvey's determinants are generally denoted by dk. Okay, so therefore the values of this dk, and here this k is varies from 0 up to n, okay, or 0 to n, and all the decay must be positive. So that means we say that the value of decay must be greater than equal to 0. So that means decay to be positive. So this is the sufficient conditions, and when these two conditions, and when all decays are greater than 0, at that time we say that all the roots of characteristic equation must be located in the left hand side of the S plane, and hence your system become stable. So in this way we can determine the stability of the system by using Harvey's determinant. Okay, then how is the Harvey's determinant matrix H? How we are going to prepare it? Okay, so please note down this. So the Harvey's determinant is denoted by capital H, and this capital H we are going to form by using the characteristic equation. Form this Q of S. Okay, so this will be your Q of S. Here A0 S raised to n plus A1 S raised to n minus 1 plus dash 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 up to an. And from this, you are going to find, prepare this H. So how to prepare H? Okay, so first of all, you just take down all the odd terms of your characteristic equation, that is A1, A3, A5. So first row of your Harvey's determinant H is the term A1, A3. Okay, so all the odd term A5 dash 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 up to A2n minus 1. Okay, so please remember this first term, first row always consisting of odd term in the Harvey's determinant. Okay, then the second row of your Harvey's determinant is the consisting of all the even terms. So it may start with A0, then A2, A4 up to dash 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 A2n minus 2. Okay, then नेक्स्ट टर्म इज 0 हियर. देन अभी थर्ड रो जो होगा वो प्रिपेयर करेंगे आप, जो भी आपका पहला ऑड वाला पहला जो रो है वो एज इट इज. ओके, सो ये आएगा A1, A3 up to dash 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 A2n minus 3. Then 2 0 we are adding here, and then even terms we are adding. Okay, so इसका ये तो 2 0 होगा, तो ये A2 से स्टार्ट होगा. तो here is A2 dash 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 A2n minus 4. Okay, so up to 0 term you can complete it. So dash 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 this could be 0, dash 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 this could be 0, dash 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 this could be 0, and dash 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 the last term could be an. तो an आना चाहिए, वहां तक आपको h फॉर्म करना. Okay, so this is the process, and this value of h, okay, or this h root Harvey's determinant, so all the values of decay to be greater than 0. So now how to find the value of decay? Okay, so you see this will be your first decay. So when k is equal to 1, you will get, so decay when k is equal to 1, you will get d1. So d1 is equal to a1 into the value of a1. And when you say that k is equal to 2, so here you will get d2. So how to find the value of d2? So for that purpose, next 4 element, so this will be your d2. Okay, so here d2 will be given by a1, a3, a0 and a2. So this will be your d2 value. Similarly, you can find d3. So a5, a4, a6. So this will be your, so when k is equal to 3, the value of d3 will be given by a1, a3, a5, a0, a2, a4, 0, a1 and a3. So this could be your d3. So in this you can find the decays, and then you just solve this matrices. So this decay must be greater than 0, so d1 must be greater than 0, this d3 must be greater than 0. So when all the decays are greater than 0, so that means your necessity condition is satisfied, and hence sufficient condition is also satisfied. That means no one roots is lie on the left hand side of the S. And in this way we can directly comment on the stability. So this is the, in short, the Harvey's determinant. But this method has certain disadvantages, so that we are going to see after solving a simple example. Okay, so when you solve the example, it will be clear to you. Okay, so please note down this capital H and how to find D1, D2, D3, or k equal to 1, 2, 3. So when you finish, you just tell me. We are going to solve one problem based on this. take down the problem. So here characteristic equations are given. F of s is equal to q of s cube plus s square plus s raised to 1 plus 4. So we have to find the stability. Find the stability. Find the stability using Hurwitz's method. Yes, हो गया सबका? Yes, have you finished it? Hello?
Yes, sir.
Okay. So solve this problem by using Hurwitz's determinant method. So here characteristic equation is given to you. So you just write down the standard form of characteristic equation. And what is the standard form of characteristic equation? Here q of s equal to a0 into s raised to power n. So what is the value of n here? So in general it is a raised to a0 into s raised to power n plus a1 into s raised to power n minus 1 plus dash 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 up to an. Okay, so you just compare your given characteristic equation with this. So first coefficient is a0. Here s, what is the value of n? Highest power of n, that is 3. So therefore a0 into s raised to power cube plus a1 into s raised to power 2 plus a2 into s raised to power 1 plus a3. Okay, and which is equal to 0. Okay, so this is your q of s, and from this q of s we have to prepare our capital H. Okay, so let's do it. First of all, write down the H. So capital H, Hurwitz's determinant. How to prepare Hurwitz's determinant? First रो कैसे मिलता है आपको? From the characteristic equation. Always we got in the Hurwitz's determinant we require the odd term. and which are the odd coefficient terms in your characteristic equation? A1, A3. Okay, so odd term corresponding to first row in harvest determinant. Okay, so these are your elements of first row, A1 और A3 दो ही मिलेंगे. नेक्स्ट आएगा तो 5 रहेगा, तो फिफ्थ टर्म इज 0. तो therefore यहाँ पर मैं इन जनरल लिखता हूँ A1, A3, A5. सेकंड रो के एलिमेंट क्या है? इवन टर्म A0, here is A2, और कोई टर्म नहीं है. So these are the element corresponding to second row of harvest determinant. These are even element. Okay, so आएंगे आपके A0, A2, नेक्स्ट अगर रहेगा तो A4 स्टैंडर्ड फॉर्म में. A4 है नहीं, यहाँ पर 0 आ जाएगा डायरेक्टली. देन एक 0 ऐड करके नेक्स्ट आएंगे A1, A3 like that. Okay, so this is your H. So now prepare final H. What is the value of A1 here? The coefficient A1 is 1. So what is the coefficient of S square? Here S square coefficient is 1. So here is 1. Then A3 coefficient A3. So A3 का coefficient क्या आएगा? It is 4. Then A5 है क्या कोई? नहीं है. So therefore it could be 0. तो 140. यहाँ तक किसी को डाउट है? प्लीज चेक इट. And second row element A0. A0 element, compare this. A0 coefficient is, here is 1. So A0 is 1. A1 coefficient is, A1 corresponding to, sorry, A2 coefficient. So A2 coefficient is the coefficient of S1, again 1. Then A4 है नहीं, therefore it could be 0. Then how to prepare next? Add 1 0 and then odd elements. You can directly add 1 4 according to this matrix. So this is your H matrix. So in this way you can prepare a H matrix from the characteristic equation. Do you have any doubt in this? How to prepare H? Because आपका एक बार H correct हुआ, so you can easily determine the determinant. Yes, किसी को doubt है? If not, very good. अगर है फिर भी very good. Yes, यहाँ तक हो गया? H हो गया सबका? Yes or not? Okay. So tell me how to prepare DK. So what is the sufficient condition? All the DK must be greater than 0 चाहिए. So this is your necessity condition. और DK H से कैसे find करते हैं हम लोग? So let's say K is equal to 1. So here D1. So D1 कैसे मिलेगा element? So it's just first element of your H matrix is nothing but D1. Okay, so here the value of D1 is 1. Then write down the value of DK. Here is 1, so that means DK must be greater than 0. So necessity condition is satisfied. Okay, so determine the determinant of this. So determinant of 1 is 1. Then similarly, D2 element, K is equal to 2. So here is your second determinant. So next 4 element. Okay, so write down the determinant here, 1 4 1 1. What is the value? Solve this determinant. Here 1 into 1 1, 1 minus 4. It could be minus 3. So whether DK is greater than 0, DK is greater than 0, this condition is not satisfied. Okay. So here we got decay to be negative. So that means this condition is not satisfied. तो आप इसके ऊपर ये भी लिख सकते हो not satisfied. Okay. Then third रहेगा, तो थर्ड आएगा आपका पूरा मैट्रिक्स 3/3. और कोई एलिमेंट बचा है क्या? नहीं. तो D3 is your third determinant. 1 4 0 1 1 0 0 1 4. Tell me the value. Solve this determinant. Tell me the value. What is the value of D3?
-12.
Okay. It could be -12. So again we got -12. So that means again it is not satisfied. Not satisfied. Okay. So what are your observation whether your system is stable or unstable? Can you directly comment from this D1, D2, D3 value on the necessity condition and sufficient condition? Sufficient condition क्या है? All root must lie in लेफ्ट हाफ ऑफ यस प्लेन. और ये कंडीशन कब सेटिस्फाई होगी? when necessity condition is satisfied. And what is necessity condition? All the decay must be greater than 0. That means all the decay must be positive. तो यहाँ पर सेटिस्फाई हुई है क्या? सेकंड नेसेसिटी कंडीशन. तो नेसेसिटी कंडीशन सेटिस्फाइड नहीं हुई, इसलिए sufficient condition भी satisfied नहीं होगी. So that's why we say that our system is unstable. Okay, so therefore आप इसमें लिख सकते हो सिंगल लाइन स्टेटमेंट. राइट डाउन. कैसे लिखोगे कंक्लूजन? whether your given system is stable or unstable by using Harvey's determinant method. So it observed that here as the values of decay are negative, hence the necessity condition is not satisfied. Okay, hence the system is unstable. So that means decay is not satisfied, hence all roots of your characteristic equation may not lie on the left hand side of the S plane. Some of the roots may lie on the right hand side of your S plane, hence your system become unstable. Okay, so in this way we can determine a stability of a system by using this Harvey's determinant. Is it clear to you, everybody? Take down the second problem. Let's say your f of s, that is characteristic equation, is given by s cube plus 8s square plus 14s plus 24, which is equal to 0. So find the stability using Harvard's criteria. Find stability using Harvard's determinant method or Harvard's method. Please do it and tell me the value of stability. First of all, tell me the value of H. And then tell me the value of dk. Hello? Whether given system is stable or unstable? Yes? Yes?
Stable system.
It is stable system. So what are the values of dk you are getting? D1 is 8. Tell me the value of D1, D2,
Yes, sir.
D3.
Yes, sir.
D1 is 8, D2 is
88.
88 and D3 is 2112.
2496.
Okay. So that means all the values of D1, D2s are greater than 0. Okay, so therefore necessity condition is satisfied, dk to be greater than 0. So therefore sufficient condition is also satisfied. So the sufficient condition satisfied means what? Whatever is the location of the roots of given characteristic equation, so all the location of the roots are lie in the left hand side of the S plane. So that is why your system become stable. In this way we can determine the stability. Okay, but what are the difficulties of this? Yes, anyone? ये मेथड की डिफिकल्टीज क्या होंगी?
Lengthy.
अभी ये थर्ड ऑर्डर तक सिस्टम है तो आपको डिटर्मिनेंट थर्ड ऑर्डर तक मिलेगा. 3/3 डिटर्मिनेंट मिलेगा आपको मैक्सिमम। लेकिन मैं अगर 5th ऑर्डर, 6th ऑर्डर, 7th ऑर्डर सिस्टम का स्टेबिलिटी आपको डिटरमाइन करने के लिए बोलता हूँ बाय यूजिंग दिस मेथड, तो will it be easy way to solve 5/5 matrix, determinant of 5/5 or 6/6 matrix? Whether it is easy one? No. So as the order of the system increases, the complexity of the determining the stability is also increases, because we have to solve the determinant of higher order. Okay, so that is the first difficulty associated with this. And second major difficulty is that, can we comment on how much poles are lie on the right hand side of the S plane? ये कोई इंफॉर्मेशन हमें मिलती है क्या? हम सिर्फ जज कर रहे हैं कि सब रूट लेफ्ट हैंड साइड में है। अगर अनस्टेबल है तो कितने रूट राइट हैंड साइड में, ये इंफॉर्मेशन हम लोग डिटरमाइन कर सकते हैं क्या बाय यूजिंग दिस हार्विस डिटर्मिनेंट मेथड? नो। Okay, so these are the difficulties associated with this Harvey's determinant. Okay, पहला है कि complexity as the order of the system increases, complexity increases. Second है how much roots are lie on the right hand side of the S plane in case of unstable condition that cannot be judged. और third है अगर कोई रूट इमेजिनरी एक्सिस पे आता है, okay, so it is difficult to judge whether your system is marginally stable or not. Okay, so that will be the third difficulty. So therefore all those difficulties will be removed by the next method, which is called as Routh-Hurwitz criteria method, or sometimes this method is also called as root array method. So that we are going to see in the next lecture. Okay, so Routh-Hurwitz method. Okay, and before discussing with this Routh-Hurwitz criteria method, we are going to see the impulse response and the step response for different location of the roots in the S plane. मतलब S plane में आपके पोल अगर रियल इमेजिनरी एक्सिस पे है या फिर कॉम्प्लेक्स पेयर ऑफ पोल है अवे फ्रॉम द S plane, so what is the nature of stability, whether your system is marginally stable, absolutely stable, like that. Okay, so depending upon the location of the roots of your characteristic equation, how is the stability can be classified. So that we are going to see first and then go for Routh-Hurwitz criteria. Okay, so today we stop here, and again I want to give you one message. Please form your project group up to Thursday and convey your group names to Professor Kankale sir. Or if you have any doubt or difficulties, you can contact me. Okay, my area of interest is electrical power system and power quality. Okay, again, if you want to do some sort of hardware project, so again hardware projects are welcome, Arduino based or Raspberry Pi based. Okay, or if you want to do the project related with artificial intelligence, that also welcome. Okay, so depending upon your area of interest, okay, you can form your group and give the or approach to respective guide. Okay, so you can आप लोग कांटेक्ट भी कर सकते हो रिस्पेक्टिव गाइड को कि सर हमें आपके अंडर प्रोजेक्ट करना है, then accordingly you can give your project group names to Kankale sir and tell them the guide name. तो if possible आपको जो गाइड चाहिए वो मिलेगा. ओके, तो सबको फर्स्ट प्रेफर, मतलब अभी एक गाइड के पास में 4 ग्रुप आए तो जो पहले अप्रोच होगा उसको प्रायोरिटी मिलेगी. Okay, so like this way we can allot a guide. Okay, okay, thank you. So today we stop here. Do you have any doubt?